Hello everyone, welcome to the next section, Convolutional Neural Networks. In this section, we will first look at the origins of convolutional neural networks. Then we will implement 2D discrete convolution. Finally, we will learn about transfer learning. Now we move on to the first video of this section that deals with origins of convolutional neural networks. In order to understand convolution, we will start by studying the origin of the convolution operator, and then we will explain how this concept is applied to the information. Convolutional neural networks, CNNs, developed while multilayer perceptrons were perfected, and the first concrete example is the neocognitron. We will now learn about convolution to understand about convolutional operator. Convolution is basically an operation between two functions, continuous or discrete, and in practice it has the effect of filtering one of them by another. You must be thinking what these filtering capabilities have to do with machine learning. The answer is that with filters, we will be able to build network nodes that can emphasize or hide certain characteristics of our inputs, so we can build automatic custom detectors for all the features, which can be used to detect a determinate pattern. Now, let's review the formal definition of the operation and a summary of how it's calculated. This is the common definition of the operation. We will now describe the steps needed to apply the operation and how it combines two functions. We first flip the signal. Here, -t is a part of the variable. We then shift it. The t present here is summing factor for gt. Next step is to multiply it, f and g. The last step is to integrate the resulting curve. This is the less intuitive part, because each instantaneous value is the result of an integral. In order to understand all the steps involved, let's visually represent all the steps involved for the calculation of the convolution between two functions, f and g, at a determinate point, t0. This intuitive approximation to the rules of the convolution also applies to the discrete field of functions, and it is the real realm in which we will be working. So let's start by defining it. Now it's time to learn the way in which we normally apply the convolution operator, which is through kernels. Kernels and convolutions. When solving practical problems in the discrete domain, we normally have 2D functions of finite dimensions that we want to filter through another image. This discipline of filter development studies the effects of different kinds of filters when applied via convolution to a variety of classes. The most common types of function applied are of 2 to 5 elements per dimension and of 0 value on the remaining elements. These little metrics representing filtering functions are called kernels. The convolution operation starts with the first element of an n-dimensional matrix, usually a 2D matrix representing an image, with all the elements of a kernel. Applying the center element of the matrix to the specific value we are multiplying, and applying the remaining factors following the kernel's dimensions. The final result is, in the case of an image, an equivalent image in which certain elements of it, for example lines and edges, have been highlighted, and others, for example in the case of blurring, have been hidden. Stride and padding. When applying the convolution operation, one of the variations that can be applied to the process is to change the displacement units for the kernels. This parameter, which can be specified per dimension, is called stride. In the image, we show a couple of examples of how stride is applied. In the third case, we see an incompatible stride because the kernel can't be applied to the last step. Depending on the library, this type of warning can be dismissed. The other important fact when applying a kernel is that the bigger the kernel, the more units there are on the border of the image matrix that won't receive an answer, because we need to cover the entire kernel. In order to cope with that, the padding parameters will add a border of the specified width to the image to allow the kernel to be able to apply evenly to the edge pixels, elements. Here you have a graphical depiction of the padding parameter. After describing the fundamental concepts of convolution, let's implement convolution in a practical example to see it applied to real image